today we're going to start with probabilities using area. So basically here, what we do, it's like the same thing as what we learned earlier, where we looked at probability on the number line, except it's two-dimensional and it's with area instead of the number line. So here, using areas, we can calculate probability in essentially the same way as length. And the formula is still the same, but the probability being the successful area over the possible area. So basically it's like the same thing except for the fact that it's area instead of length. So let's start with the problem. Point C is chosen at random on a 5 by 5 foot square table. A circular disc with a radius of 1 foot is placed on the table with its center directly on point C. So what is the probability that the entire disc is on top of the table? So here, basically what we want to find is we want to find the probability that the whole thing is going to be in the area of the table. So basically, the total outcomes region is easy. It's just the surface of the table. So first you have to calculate the total outcomes region. So 5 feet by 5 feet is 25 feet squared. So we just over 25. And then now we have to find the successful outcomes region, which is a bit harder. So we can draw like a diagram. So here's our successful region. Here's our possible region and our successful region. We want to have this 1 foot circular disc. The whole thing has to be on the table. So basically we can have this, and this would be correct. But like if part of it is off the table, then this is not right. So basically what we can see from this, the entire disk will only be on the table if and only if C, the center, is at least 1 foot away from each edge of the table. So basically we can draw like a little square here where the center can be. So it has to be 1 inch away from the edges of the 5 foot table. So basically now we have this 3 foot region. So basically, if the center is inside the 3 foot region, the entire disk will be inside of the table. So what we do now is we're going to calculate the area of this region, which is 9. So the probability is going to be 9 over 25. So I'll just give you guys some practice problems. These aren't like explicitly with area, but you can just like draw area diagrams in order to solve these. And if you guys have the answers, can you please private message the host, which is me? All right, let me go over these. So these are like area problems, but you can use diagrams to draw out the areas. So this might seem a bit confusing at first. So suppose two numbers x and y are each chosen so that x is between 0 and 1 and y is between 0 and 1. So what's the probability that x plus y is greater than 3 halves? So in here, since there's nothing discrete in this problem that can be counted, we need to use geometry. So basically in every problem where you don't count items and you count area, like if there's an infinite amount of things you have to count, then you would have to use geometry. So the total outcomes region is the region in the xy plane. So let me just draw this first. So here's a unit square, and the total outcome region is the region um, where basically the entire region in this unit square. So then it would be over 1. And we need x plus y to be greater than 3 halves. So to do this, we will have to be the region inside the square, which is above the line x plus y is equal to 3 halves. So basically, if you know how to graph lines, you'll know that you can graph it and the line will end up looking like this. And since x plus y has to be greater than 3 halves, it will be this area. And then you can tell that the area of the triangle is 1/8. So the answer would be 1/8. So that's the probability for the first one. And now for the probability, the second one, we're going to draw another diagram. So once again, because we have infinitely many possibilities, we won't be able to use regular counting, so we need to look for a geometric approach. We can make a graph plotting. You can calculate the area since each side is 1/2 and it's a triangle. So yeah, you just multiply the sides. All right, so let's draw the second one. So since it gives us the arrival and leave times, basically it says between noon and 1 p.m. So we're going to draw like a unit square thing here. So 12, 1 o'clock. So me and friend. Basically what this thing is asking is that we need to find the region of time where both of these people arrive 15 within 15 minutes of each other. So this part might seem confusing at first, but we have to try some examples. So like we could say that if I arrive at 12, my friend has to arrive between 12 and 12:15 and stuff like that. So we can basically just draw the two lines to look like this. And basically this is 15 minutes long. So we can calculate the area of this thing, and the probability that we will meet is 7 out of 16. So if we try the examples, we can like find the length of the diagonal thing, which is this, and then we can just use that and calculate the area of the shape, which is 7/16. Move on. So the summary is we can use the summary of this and the probability with the lines is we can use geometric tools to solve certain problems. We can use it in situations where we have infinitely many outcomes, where we can draw a diagram to represent the problem. So like you have infinitely many times. You can't just like count a certain amount of times. And if we are trying to compute a probability where the outcomes are continuous, like infinite. Yeah, I didn't write 11. I wrote 12. Well, they're basically these are like infinite possibilities, so it's probably better if you draw it out, but there would be other ways, but they would probably take more effort. So here, let's move on. Now we're gonna learn about expected value. So you should know what a mean or average is, which is like the average of multiple numbers. So if we extend the concept of average to the outcome of a random event, that is expected value. So expected value is the average thing we would get if we did a large number of trials for any experiment. So basically, let's just suppose we flipped a coin. If we win, we would get $2, but if we lose, we would lose $1. We would expect to get the same amount of heads as tails. So if we flip the coin 100 times, we would win 100 and lose 50. Basically what we expect. So we expect to win $50. And since there are 100 flips and we win $50, we would expect to make around 50 cents per flip. So basically that's what expected value is, the average of all the outcomes of a situation. So I have an example problem here. I have three $20 bills and one $10 bill in the bag. What is the expected value if I pull a random dollar bill out? So here we have to think of this as like an average or something of multiple numbers, right? So basically what we do here is we have to see like the probabilities of each of the outcomes. So since there's $4 bills and three of them are 20, and expected value is the average of all the outcomes of an experiment if you were to do a lot of them. It's like the average of the outcomes. So here, since there are $4 bills, there's three $20 and one $10. We can tell the probability of reaching a $20 bill is 3/4, and the probability of getting a $10 bill is 1/4. So basically, we can write like 20. The probability of getting 20, it's like 75. It's 3/4. So it has three times as much weight as the $10. So basically what this is we have to find the average value. So what we would expect if we pull it out is we basically expect a value that is closer to $20 than $10. So we can find this. Yeah, we can find this by writing three 20s, since 20 has three times the weight, and 10, we can find the average of this. So we add these, we get 70. We divide this by 4, and so we divide this by 4 and we get 17.5. So yeah, that's basically how you do expected value. Also notice how 17.5 is not like, it doesn't match any of the other values. Like it says 20 and 10, but it doesn't say 17.5. But you know that it's the average, so it would be basically like the middle point or something like you would expect, the average you would expect to get, which with each poll. So yeah, I have some practice problems here. I'll give you a few moments to do these. Basically, the second question says, it tells you the expected value, and you're supposed to find the weight of the twos and the weight of the sevens. So like, how many sevens are there compared to twos? All right, so let's go over these practice problems. So here, what is the expected value of a roll of the standard six-sided die? So basically here, each outcome of rolling a six-sided die has probability 1/6, and all the possible outcomes are 1, 2, 3, 4, 5, and 6. So since they all have the same probability, we can just find the average of them without having to add any weights. So we just go find 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6. And what we would get 3/5. I mean 3.5. So note that since each outcome is equally likely, we can just find the average of all of the outcomes. Other problems aren't going to be like this, and you have to add like weights, which means you have to write it multiple times. So the second problem, suppose I have a bag with 12 slips of paper. Some have the number 2, and the rest have the number 7. So if the expected value of the number shown on the slip randomly drawn from the bag is 3.25, how many two slips are there? So basically we can, let's just use the variable x to denote the number of two slips we have. And then there are 12 minus x slips with the 7 there. So the 2 is x and 7 is 12 minus x. So basically the probability of drawing a 2 is x over 12, and the probability of drawing a 7 is 12 minus x over 12. So the expected value is, we have to weight this like x, 2x over 12 plus 84 minus 7x over 12, which is equal to 84 minus 5x over 12. So since we want this to be 3.25, basically this is like a equation now, and we can simply solve this by multiplying both sides by 12. 84 minus 5x is equal to 39, and now we can just solve it from here. We get 5x is equal to 45 and x is equal to 9. So there are 9 2 slips there, and there are 3 7 slips. All right, I have some more practice problems. The second one is pretty hard since there's infinite outcomes, but like once you get it, it's pretty straightforward.
Wait, the expected value for what? Like in the first problem.
The expected value of what you what you win with each flip. Send your answers to Ethan Xiao, because I'm the host. All right, I'll go over the problems now since I'm not getting any more answers. So suppose you have a weighted coin in which heads comes up with probability 3/4 and tails with probability 1/4. If you get heads, you win $2, but if you get tails, you lose $1. What's the expected value? So this is basically the same problem as the example problem that we just did. So by definition, we multiply the outcomes by the respective probabilities and we add them up. So basically, since um, the $2 is 3 times more likely to happen than losing $1, we just find the average of 3 2s and 1 - 1. So we add these together and we divide it by 4. And what we get is we get 5/4 or $1.25. So now we go to the second one. You're playing a game in which the prize pool starts at $1. On every turn, you flip a fair coin. If you flip heads, then the prize pool doubles and the game continues. If you flip tails, then the game ends and you win the prize pool. What's the expected value of your winnings? So basically, this game is a paradox because like you could get extremely lucky and you could get like infinite dollars or something, or you could just walk away with $1. But we will approach this just like any other problem, except so we can list all of these we can list all the outcomes. So first you lose if you lose the first one, you'll just win one. Then you'll have 2, 4, 8, 16, 32, all the way to 2 to the power of n, where um n is the one where you get tails. So basically, to calculate the winning amount, we have to multiply all of these numbers by their probabilities and then add them together. But the problem is you're going to have numbers that are really high and you're gonna have like infinity. So since you have infinity, the expected value is going to be infinity since the possibilities never end and they're going all the way up to infinity, and you know that anything that you do to infinity will still be infinity. So the answer is infinity since all of the since the possibilities do go up to infinity. Yeah, this one's a trick question. Since basically it never ends and you're always adding new numbers. Well, since you have all of these probabilities, it is actually infinity. The paradox is, well, it's not, that's not the chance though. This is the expected value. Expected value is the average of all your expected winnings. So the
Oh,
paradox,
that's why I got stuck on it.
yeah. So the paradox is that there's no way this game could exist in real life, since you will get one of the outcomes with finite money, but the expected value is infinite since it's possible to get really lucky and like get infinity dollars. But like that's not gonna happen in real life. Since no real person has an infinite money supply to pay you, in real life you would probably just win a finite amount of money. But the expected value is still infinity. So basically, the summary is expected value or expectation is a generalization of the concept of mean or average, in which the probability of the various events occurring is taken into consideration. If the possible events have probability like this, and the events have values x1, x2 to xn, then the expected value formula is you basically just multiply all of the probabilities with all of their respective outcomes, and then yeah, if all the events are equally likely, you can just find the average. And if you have like a paradox problem where all of the where it's possible to get like infinite dollars, it doesn't matter what the chances of getting it, the expected value is still going to be infinite because you have like infinite possibilities of money. So let's move on. Now we're going to learn about Pascal's Triangle, which is a good gadget to learn about combinations and stuff. It's more than just like a pattern of numbers. It's also a list of counting relationships, and it's basically a grid of counting numbers. So I'm going to draw Pascal's triangle. So what this is basically we start with 1, and then we're going to make each number, we're going to add each of the two top numbers together and basically just like have that number. So 1 plus 1 is 2. And since there's nothing here, we just do that. And so basically, the next number is going to be the top two numbers added together. So we have 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and 1, 6, 15, 20, 15, 6, 1, and so on and so forth. So basically, this is what Pascal's triangle is. So you so this is basically what it is. Do you recognize some of the numbers here? Um, so basically here, uh, basically in this triangle, some of these numbers, so basically some of these numbers, all of these numbers are going to be the combinations of all of their things. So what we do is we can just find out that these are all combinations. So the first row is 0, the second row is 1, the third row is 2, the fourth row is 3, 4, 5, 6, 7. And so basically the first one is 0, 0, 0, choose 0, and then we have like 1, choose 0, and 1, choose 1. Looks like a 4. And then we have 2, choose 0. This one is 2, choose 1, and then 2, choose 2. And then the pattern goes on. So you can see that, right? All of these numbers. So basically, all of these numbers are just combinations. So what this basically is we have like the top number, the number of the row is going to be the top number minus 1. So like this row over here would be the 7th row. So it would, this row is like the 8th row of the triangle. So the top number is 7. And basically, if you are stuck on combinations, you can just create this triangle, and then you can find out the combinations through this triangle. So now we have how many paths are there to get from the top number down to the how many paths are there to get, how many paths are there to get from the top number to both of the 4s if you can only go down. So what we're doing here is basically we can get from the top number to one of these things, but like you can only go this way or this way. So let's just look at this. We must take a total of 4 steps, since the circle dot is 4 rows below the top dot. So of these 4 steps, 3 of these steps must be to the right and 1 of them must be to the left. So basically, we're just doing like the paths thing on the grid again, but with Pascal's triangle this time. So since we have 1 down and 3 right, we're just doing 4, choose 1, and the answer would be 4. So there's 4 ways to get from this 1 to this 4. 4. So how many paths are there from the top 1 to the 6? So here, there are 5 steps we must take to get from the top 1 to the 6, and there are 3 rights, and there are 2 rights, and um, there's 2 rights and 2 lefts. So basically, we actually have 4. We have 4. Let me just do that again. We have 4 steps to get to the 6, and there's basically 2 rights and 2 lefts. So we're doing 4, choose 2, which is 4 factorial over 2 factorial times 2 factorial, and that would be 6. So then there's 6 ways to get from the 1 to the 6. Oh yeah, I didn't elaborate there, but these aren't the ones we're looking for. So yeah, it would actually be 6 too. So if you guys notice something, it's that basically if we're getting from the top number to one of these numbers, the number of ways to get there is going to be the same one. So if we wanted to get from 1 to 20, there would be 20 ways. If we wanted to get from 1 to 35, there would be 35 ways, and so on and so forth, which is interesting. So we know that Pascal's triangle is basically a list of combinations, and basically if we go from 1 to that number, we're basically using the combination. So now we know that all the numbers in Pascal's triangle are all combinations. So how does computing paths on Pascal's triangle correspond to our original construction, where we just added the numbers to get to the next row? So let's label just 2 points above something. Let's just say these 2 3s and the 6. So we know that 3 plus 3 is 6, and that's why we initially threw the 6 there. But note that every path to the circle dot has to pass either A or B. So if we wanted to get from 1 to 6, we have to have passed through one of the 3s. So the number of paths to the circle dot is basically the number of paths to one of these versus the number of paths to another one. So that's how we made it in the first place. We obtained every number in the triangle by adding the two numbers above it. And also recall we started with the 1, and but this works with our path walking explanation too. There's exactly one path from the top dot to the top dot, which is to do nothing. So we can see that the number at each entry of Pascal's triangle is the number of paths from the top to that point in the triangle. So basically that would be n choose r. So the entries are the combinations, which is n choose r. So I have some practice problems for you guys. Basically what this is we saw Pascal's triangle, right? So you just need to calculate all of the you have to calculate all the combinations there and basically just prove that it's correct. All right, I'll just go over these now. So let's verify that these are correct. So the choose one choose 0 plus 1 choose 1 is 2 choose 1. So basically we can see that 1 choose 0 is 1 plus 1 equals 2, which is right. So 4 choose 2 plus 4 choose 3 is 5 choose 3. 6 plus 4 equals 10. And 7 plus 4, 7 choose 4 plus 7 choose 5 equals 8 choose 5. 35 plus 21 equals 56. So if you notice, something interesting is really going on here. Since you can see like a pattern where basically, if you look at this, 4 choose 2 plus 4 choose 3 is being 5 choose 3. You can see that the 2 plus 3 is always 3, and the 4 plus 4 is 5. This also goes as the other ones as well. So basically, we're adding two combinations with the same top number, and the bottom numbers are different by 1. The result is a new combination where a top number is +1 and the bottom number is equal to the larger one. So our rule here is n minus 1 r minus 1 plus n minus r1 choose r is equal to n choose r. So that is our new rule. It's called Pascal's identity. So this is our new rule. This identity can be used in a number of cases like some counting problems. So now we're going to learn about another combinatorial identity. So if we added the numbers of the rows, something interesting happens. So we have 1, 2, 1 plus 2 plus 1 is 4, 8, 16, 32, 64, 128. So now we learned from this that the sum of each row is a power of 2. So we have, so since this is the 0th row, this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 3, and so on. So now we know that another interesting identity is that choose 0 from n plus choose 1 from n plus so on until choose n from n is going to be 2 to the power of n. So if you have like all of the choose from 7s added together, it would be 128 and stuff like that. So that is pretty interesting. And you probably don't need to know it in like competitions, but it's just pretty useful. So our summary is Pascal's triangle is constructed by starting with a 1 at the top, and then each number below it is calculated by adding the top two numbers. The numbers in row n of the triangle are just combinations of the n, and basically the n is the top number, while like you have 0, 1, 2 so far until you reach n on the bottom. So we learned Pascal's identity, which is basically this plus this equals this. So this one's also pretty useful as well. If you don't want to manually add the combinations, then you can use Pascal's identity. So I'm going to end class here. I'll see you next week. Bye.
Bye.
Thank you. Bye.